So welcome to all to this workshop on Spark for machine learning. I'm Jean-Philippe Moreau from the BNF, and I'm going to give the floor very soon to our two speakers today, Audrey and Michael from the PLA. Before giving the floor to our presenter, a few reminders about this Zoom call. Please make sure your microphone is on mute when you're not speaking. The workshop is being recorded and we'll resend the link very shortly. Regarding the QA session, please put your question on the chat box. I suppose, but Audrey will process this. You can raise your hand during the workshop and ask a direct question to the presenters. So, Audrey, it's to you.
Great, thank you. All right, here we are. I hope you can all see that. Welcome to our workshop. This is the introduction to Spark for machine learning. I hope you all will enjoy this presentation. We're very excited to be here with you all this morning. Well, I guess it's this morning for us because we're in the United States on the East Coast, and I honestly have no idea what time it is for the rest of you. So whatever time of day it is for you, I hope it's a good time, and welcome to our presentation. All right, so we're going to start out by introducing ourselves. I'm Audrey, and I'm joined by Michael Dallabita. Michael is the Director of Technology at DPLA, and I am one of the software developers there. And you can feel free to connect with us. I've thrown up our Twitter and our LinkedIn and our email addresses. And so you can feel free to follow up with us after the presentation if you have any questions or anything like that. And we are from the Digital Public Library of America. So what we're going to talk about today, we're going to start by talking about what Spark is and why you might choose it. We're going to go over the basic Spark abstractions and APIs, and we're going to intersperse our talking with some code demonstrations. So the first one, we're going to do a case study about image dimensions. Then we're going to talk about the architecture of Spark. Another code demonstration about near duplicate detection. Then we're going to go back to presenting and talk about the Spark ML or machine learning library. Last code demonstration is about topic modeling. And then finally, we're going to talk about running Spark in the cloud. So we have a lot to cover, but I think it's going to be pretty fun. And if you don't have a strong coding background, or if you don't have a strong machine learning background, or if you're not a data engineer, don't worry. We've tried to make it pretty broadly accessible to everyone. But if there's a part of the presentation that is just not in your wheelhouse or not interesting, then just bear with us, and hopefully it'll circle back around soon to something that you are having more fun learning about. So. If you want to code along today, this is totally optional. If you want to code along because that's how you prefer learning, then you can. You should be able to sign up for a free trial of Databricks Community Edition if you go to this link. Maybe, I don't know, Michael, could you drop that in the chat? I don't really have my chat window available to me right now. But anyway, that's the link. And I think somebody said they were having trouble this morning signing up for a community edition. So I hope that's not the case for too many of you. But when you sign up for the trial, do click on the community edition, and there's two options. One of them is community edition and one of them is like try for free. So click community edition because that's the really, really free one. And just to sort of throw it out there, we don't actually use Databricks at DPLA. Databricks is a proprietary software that is pretty popular for people who use Spark. And we're not, promoting it or anything. We just thought that if people could get in and log in for the community edition, it's a fast and easy way to get up and running with Spark without having to worry about doing installations of any special software on your local machines. So we thought we'd try it for this demonstration, and we'll see how it goes. Alternately, if you have a local Spark installation on your laptop or whatever computer you're on, you can feel free to follow along. Using just your PySpark REPL on the Spark installation. And I will briefly show you how to do that once we start coding. And if you don't want to code along, that's fine too. We have all of the code is freely available. All the data is freely available. You should be able to download it quite easily, so you can take it away and look at it later if you don't want to actually be like typing along during the presentation. Okay, so I'm going to start out with what Spark is. Spark is a data processing engine. It's best known for being good for using with big data. So you can perform complex analysis and transformations of very large data sets with Spark. It's also a cluster computing interface, which is fault tolerant and scalable, and we'll get into that quite a bit later. It's open source software released into the Apache license, so it's freely available for anybody to go and grab and use, and if you feel so inclined, contribute to the project. And it's widely, it sort of came about as an alternative to MapReduce. It was addressing some specific challenges with using MapReduce, and it grew up as an alternative framework to MapReduce. And specifically, it improves ease of use and execution times in the right context compared to MapReduce. If you're familiar with MapReduce. If you're not familiar with MapReduce, don't worry about it. So the history of Spark, it was started in 2009 at Berkeley, and in 2014 it was donated to Apache, and it is now one of Apache's sort of big flagship softwares. And it's used today by hundreds of companies, and I think it's used by a few libraries and galleries, museums, and archives around the world too. So some use cases from industry. People use Spark to build things like recommendation systems for fraud detection, for doing big log processing jobs, sentiment analysis and medical research. I mean, there's a lot of examples out there. So these are just a few ways that Spark is in use in industry today. We use it at DPLA. We actually use Spark like every day. We use it for our main ETL system, extract, transform, load system. So we use it to harvest, map, and enrich very large data sets. We use it to serialize data into different formats. We use it to upload our data into Elasticsearch. We do metadata quality analysis and generating sitemaps, and we do a bunch of other little things too, but these are some of the big ones that we do on a regular basis using Spark. Okay, so why might you choose Spark? So these are the optimal use cases for Spark, the things that it really shines at. It does some pretty cool stuff with machine learning, which I think is why you're all here today. It has some interfaces for interactive analysis. So things like being able to pull up a cluster and jump into your REPL or your notebook or whatever you're using, and to do some SQL queries on your data, or to do some quick statistical analysis on your data. So it has that interactive component, which is nice for some kind of workflows. It's also really good for batch processing workflows. So that's what we usually use it for. Batch processing is, you have a large set of data and you're going to perform a bunch of transformations, and you're pretty much going to do the same transformations to the entire data set. So it's like a big data pipeline that you push your data through, and it starts out in one format on one end, and at the other end of the pipeline, you have a different output. It's good for data integration. So if you need to bring data in from multiple different sources, it has streaming interfaces. We're not going to talk about streaming today, but just want to put it out there that it does do data streaming stuff and ETL processes like I talked about. ETL, extract, transform, load, if you're not familiar with that abbreviation. So you might consider using Spark if you have one of these or several of these things. So the first is a need for speed, needing to process data very quickly, which Spark can do. If you have a lot of data, Spark can work with both structured and unstructured data. But if you have so much data that it's starting to become unwieldy and difficult to use on one machine, Spark can help you to move to a cluster situation. If you have multiple data sources, either archive data or streaming data that you have to sort of pull together and talk to each other, Spark can help with that. You have to have parallelizable tasks, which for the computer scientists in the room, you'll know what that means. But a lot of data processing and machine learning tasks qualify for parallelizable. And when Michael talks more about the the way that Spark works under the hood, it will become clear why that's necessary. You also have to have a lot of RAM. Spark is kind of a memory hog. It uses a lot of RAM during processing time. So you have to have, in some way, access to a lot of RAM. That's what we use our cloud clusters for, is to get a nice big RAM-y cloud cluster that can accommodate that. And finally, you'll probably want to have some engineers around if you're going to do production level software development. If you want to move to production, moving up to the cloud can be a little bit tricky. So it's nice to have some skilled people around who can help with that. There are times when Spark isn't the right fit. So if you wanted to really get into deep learning and neural networks, Spark has some functionality here, but it's not as built out as other systems like maybe TensorFlow or PyTorch. If you need to do fine-grained reads and writes on your data, meaning like you need to go in and change one record in one way and another record in another way, rather than applying like blanket transformations across your entire data set, then you'd be better off using something like a database. Spark just doesn't really do well with those like very, very small tunes to individual records. If you need to have, I mentioned that there was an interactive analysis interface, but it's not like persistent like a database would be. So if you need a place where there's going to be a lot of real-time interactive querying all of the time, then you might want to have something like a database or a search index instead. So what else? If you need to do streaming, but without the complex data processing, then you might pick something simpler, like a client library like Kafka or Kafka Streams. If you have really, really, really like absolutely humongous data, or if you have limited RAM, then you are probably just as well using MapReduce as Spark, because Spark sort of relies on having that the concept of being able to put a lot of data into memory in order to really shine. And if you have so much data that you can't really fit any of it into memory, that you need like enough of it into memory, then you might just fall back to MapReduce. Or you could still use Spark. And if you have really small data, like really not that much data, then you don't really need a cluster. So you might want to use Spark because if you already are using it, it's really nice for being able to do parallel processing even on a single machine, like getting a lot of tasks running concurrently. And it has some nice libraries, but you don't really need to use Spark in that case. There are a lot of other machine learning libraries that you might use instead. So some of the pros, some of the ways Spark really shines: it's good for performance, it's very scalable and fault tolerant, it's relatively easy to deploy, especially to get up and running in a local instance. When you're moving to the cloud, it's a little bit harder, but it's still not terrible. I mentioned it's open source. It's interoperable with a lot of other tools, so file management tools like Hadoop or Amazon S3. It's got good infrastructure for cloud computing. You can do data analysis and data visualization tools. It's interoperable with things that are good for cloud computing, data analysis, and data visualization. So we'll see a little bit of that in action today. But yeah, there's a lot of tools that work well with Spark. And it has APIs for several different programming languages. It has an interactive programming shell, a flexible data model, abstractions over lots of data serialization formats. So today we're going to be using text and CSV files just because they're simple and easy for y'all to download, and they're easy for a human to read if you wanted to look at the files and see what they look like in order to understand better what the code's doing. But you can also use things like JSON and Parquet and Avro, and there's a lot of different file formats that are compatible with the Spark environment. And it has a strong community of users and developers, which is nice if you have questions. Okay, there we go. There's my other slide, Spark cons. So reasons why you might not want to use Spark or think twice about using Spark. Configuration for very large jobs can be a little bit tricky, as can be debugging at scale. The error messaging is not the best. They tend to dump a whole lot of information at you to sift through. Like I said, it can be a memory hog, so you have to have the memory available to you. It doesn't have built-in file system and data visualization tools. Like I said, it's compatible with a lot of external tools, but some people consider it a downside that it doesn't have those internal to the system itself. It can be inefficient when dealing with a lot of small files. That's sort of a specific use case, but if you have that use case, be aware. It's a little bit slower and has a little bit lagging in functionality with Python and R. I mean, I don't think that's a reason why you would necessarily not use it, but something to be aware of. The native language for Spark is Scala, so it tends to roll out new features in Scala first, and then Python and R lag behind a little bit. It's not optimal for a multi-user environment. So if you have a lot of people who want to be working concurrently on the same stuff, you might then consider something like Databricks, which is proprietary, but offers that multi-user environment. And it's, I don't know, when we first wrote this down, an adolescent and changing software was a few years ago, but I think it still qualifies as an adolescent and changing software. So you just have to be aware that it's still growing. All right, so I'm going to pause here for a checkpoint and see if anybody has any questions or comments that they'd like to share. Well, I don't see any, so Michael, I'm going to over to you.
Great, thanks, Audrey. So first off, I'm going to speak about some basic Spark abstractions and APIs, which will help you understand the execution environment that Spark jobs run in, which I think it's important to understand the basic metaphors so that you know what's going on and why you might run into specific behavior if you kind of tread off the beaten path a little bit. So just to start, overall, Spark's trying to solve a problem. And the problem is that it's hard to write concurrent scalable systems using standard libraries built into most programming languages and runtimes. So if you're trying to write multi-threaded code or code where there's a process that needs to fan out across a number of threads or a number of computers, that's something that you would need to write yourself if you didn't use an environment like Spark. There's many ways to do that. Spark is what we think is a good choice, particularly for our uses. But if you were trying to write that from scratch in your own programming language, obviously you'd have a lot of work in front of you. So here is a solution. Imagine your programming environment offering a list or an array type that could be spread out among many computers automatically. So you don't really have to think about how that's going to happen. You just kind of have to say, my data is over there, load it, and it'll bring it into your cluster for you. Just to note, you can actually run it on one machine too, and it has some advantages as well, but we'll touch on that later. So just to continue with the problem solution motif, imagine if you needed to perform an operation across every record in that data and it was too big to fit on a single machine. It'd be great if you could broadcast that operation out to the data and have each computer run it on the part that it had. And the reason being is that your instructions probably are very small kilobytes of code, and your data might be terabytes or petabytes of data, and it's actually easier and quicker to move your code to the data than your data to the code. And so that's kind of the environment we're operating in here. So just for a second, I'm going to apologize. I'm going to be blurring the lines here a bit between API, language, and architecture, which is kind of ironic because this is a section called talking about abstractions. But in Spark, these can all turn out to be a little intertwined. Some languages don't have support for specific APIs, and other APIs are built around specific architectures. But as we'll see, there's one kind of main path that if you go down, you'll be good to go in whatever environment and language you want to write code in. But just wanted to apologize ahead of time for not making super strong distinctions here. So the main abstraction in Spark, or the fundamental one at least, is the RDD. And most of Spark's execution model depends on understanding what they are. So I'm going to dwell on them for a sec. The big array in the cloud gloss is my particular take on them and not official Spark marketing copy. So take that with a grain of salt, but I think it gets at the idea in a very general way. So here is the academic paper that kicked off the whole Spark ecosystem. Much like Apache Dupe was an implementation of the concepts that Google talked about in the original MapReduce paper, Spark is based on the RDD concept as described in this paper. And this is freely available online. Actually, if you look at my slides, I think there's a link to the paper in the alt text of this. So what does RDD stand for? The R in RDD is resilient. And what do we mean by resilient? When you run software on a single machine, it's easy to think of error conditions as binary states. Either your code ran or it crashed. But in the world of a compute cluster of 1,000 machines, it would be unacceptable to need to restart all their work because one machine or task had an issue. Also, with a larger cluster, you're more statistically likely to have failures. So you want a mechanism that will help you work around them. And Spark is built on abstractions that allow for redundancy to prevent against data loss and can rebuild data when it is lost. So it's going to recover if your machine goes down or your network interface dies or a disk goes south, like those sorts of problems. Okay, the first D in RDD stands for distributed. And distributed is the quality that enables Spark to work with large amounts of data with high throughput. Spark will shard and distribute data sets and their downstream computational products evenly across even hundreds or thousands of machines and keeps track of which machines are in charge of what portions of the data. And you don't have to pay attention to where the data is exactly. You just write your code against APIs where that's abstracted away. So that's terribly convenient. And the final term in RDD, and the last D, is stands for dataset. Data sets are the initial states of data we're working with, as well as their states as they are transformed into the data we want at the end. In Sparkland, every row of a data set corresponds to the same schema, although the schema might have optional fields for every row. And data sets can come from numerous sources, as we mentioned, such as CSV files, JSON, SQL databases, NoSQL stores, and other formats we'll touch on later. And each of these disparate sources can be combined in flows during the execution of a Spark job. So you can have, a database data being joined against a CSV you have somewhere else, or you can be pulling in some JSON and munging all that together in your data flow. Once they're loaded into RDDs, the details about the source of the data are abstracted away. So you don't really know, you don't have to think about the fact that here I'm working with a JSON dump, and here I'm working with the database. It's the same API to manipulate the data after that. Okay, so that's the foundational data structure in Spark, but it's not the only one. And as we'll see later, it's probably not the one you're going to be working with. It's just underneath the covers. But once you understand RDDs, it's kind of easier to understand the other major APIs and modes of working with Spark. So we can briefly touch on them so you know what's there. So here is the concept of a data frame. A data frame are data frames are higher order APIs implemented on top of RDDs. And if you're already familiar with data frames from Pandas or R, you already get the idea. Data frames are essentially a big table with your data in it, and they're wrapped by APIs that let you manipulate the data. Only Spark data frames can be distributed across an entire cluster and can be backed by any of memory, disk, and remote access under the covers. Generally speaking, they only contain specific and uniform types and data structures similar to a database table. Unlike RDDs, the data manipulation APIs on data frames are higher level and not as do-it-yourself. Also, since the Spark engine understands the composition of data frames in a deeper way than RDDs, it's able to do really terrific optimizations to the operations you can perform on them, including with working on serialized data directly rather than instantiating objects and dealing with that overhead. So there's also this notion of a data set in Spark, and I'm just going to touch on that here because you might come across it. Data set is an attempt to use the looser data model of RDDs in a context that uses some of the API and performance optimizations developed for data frames. The way they did this is smart, and they use some really good features from Scala, but it doesn't seem to be portable to Python and R in the same way as data frames are. So take data sets with a grain of salt. And here's Databricks' explanation of the three APIs we just talked about and how they relate to one another. And clearly someone at Databricks didn't put data set in their user dictionary because there's red squigglies under it. But I just wanted to show everybody this so you could get a sense of like the chronological progression that is happening here, and Databricks and Sparks kind of gloss over what the differences between them are. And I don't know if we've mentioned this yet. Databricks is the company that kind of fosters Spark's development, but obviously it's being run in a number of different places. So don't get the impression that since there's a website that charges for Spark usage that you need to use that. It's entirely open source and it's available fairly broadly. So just to summarize, I'm going to go out on a limb and say use data frames unless you know to do otherwise. Data frames have extra performance optimizations built in versus RDDs. They're a higher level API than RDDs, so they're easier to use, and they have the most cross-language support. And particularly when you're trying to prove out a machine learning workflow, you don't need sort of a lot of ceremony and things in your way. You kind of want to use really high leverage APIs to get a lot of work done. And I think that's what data frames offer out of the box. Also, there's a couple of other APIs that are built into Spark that I'm going to call meta APIs because they're not so coupled to data structures. But once you understand RDDs and data frames, it's kind of easier to understand the other major APIs and modes of working with Spark. So I'm just going to briefly touch on them so you know what's there. There is a SQL API to working with Spark data, in particular with data frames. And it's a really full-featured API that is available in a REPL or programmatically. Spark SQL supports advanced SQL idioms like user-defined functions, statistical aggregation, subqueries, and performing operations on complicated nested structures that data frames can represent. You can query all the sources you can load into Spark as if they are SQL databases and at scale with this API. And then there's Spark Streaming, which uses a micro batches mechanism to deal with data that's continuously being updated from a streaming source. And this approach lets you write similar code as you would for standalone batches, including doing things like joining to other data frames, but in real time. There's parentheses around structured here because there's actually two APIs. Writing code for structured streaming uses the dataset and data frame APIs, while streaming without structured next to it is an RDD-based API. And there's another API called GraphX, which is for working with graph structures like triples and other entity relationship-based data models. So things like social data that has a lot of interconnections and things like that. And Spark offers a way to work with that data across a large cluster and in a way that you wouldn't be able to accomplish with a single node if your data was too big for it. And finally, there's Spark ML, but that's kind of like a big chunk of this presentation, so I'm just going to mention that in this list and move on. Spark has really great cross-language support. Right now, there's 4 and actually 5 languages if you count SQL. There's Scala, which it was written in. There's R, which is a statistical programming language that some people may be familiar with that's freely available. Python is extremely popular in machine learning circles, and that's available as a first-class API. And if you want to, you can write Java too, although personally I would recommend picking one of the other languages because Java, dealing with the, because it doesn't have type inference, it can be really verbose in this case. So Spark uses an API called data source to abstract over reading and writing from different data stores. The same workflows you write against one data source are portable to others. So data sources are pluggable, so anybody can write one for what they need to get done. In fact, we've written one for OAI harvests that we use at DPLA. And a lot of data source implementations reuse work that was done for the ecosystem, the Hadoop ecosystem. So there's actually a number of them already for things like SQL databases and that kind of stuff. So you get a lot of leverage out of this API by counting on work that's already been done. And here are a few data source examples that are already built into Spark or available as downloadable libraries. Obviously, we've already talked about the fact that you can use text files and CSV files. I mentioned that you can use JSON, although it's a particular format called JSON lines, which means that every record is on a single row of a text line, a text file. So it's not going to take a 10 gigabyte JSON array and parse the whole thing and figure that out for you. It wants it in that particular format. Down there at the bottom, we've mentioned Avro and Parque before. Those are binary formats that are kind of optimized for big data issues. In particular, Parquet is a columnar format that instead of treating data in rows, it actually stores every column as a separate section of the file. And what that means is that if your code only addresses like one particular column or a subset of the columns in your data, you can actually skip over all the other data, which is really convenient for interactive querying purposes. On the data store side, I mentioned SQL databases. So anything that has a JDBC driver, which is a Java API that you can write for database drivers, can be used natively in Spark. The search index engines, Solr and Elasticsearch they both have clients. So you could write a Solr query to query a cluster of Solr nodes and bring all the data that corresponds to that query back into your Spark cluster and work with it. Big NoSQL stores like HBase and Cassandra are available too, and Hive is sort of like a Hadoop ecosystem, like a data warehouse library, and that works with Spark as well. So these are just some examples. There's actually a pretty wide ecosystem of these. Okay, we're at another checkpoint. Does anybody have any questions about what I just said? Okay, I don't see any, so I'm gonna pass it back to Audrey.
Okay, so let's do a code demo. Woo, exciting. So we're gonna take some of the stuff that Michael just talked about and put it into code and put it into action. So we are going to see in action in this code demo, the data frame abstraction. We're going to do some simple data manipulations. You're going to see a visualization integration, and we will be using for the first time in this presentation, Databricks, or if you are working with a local installation, you will be using your REPL. So the case study we're going to look at, this is all of the code demos today are based on real case studies, things that we've actually done in DPLA. So this one is a pretty simple one, but also a very important one. We have millions of image files. So one of the things that DPLA does is we aggregate data from thousands of individual libraries, archives, museums across the United States, and we put them into one big aggregation. So we have about 40-some million metadata records right now, and most of them have an image attached, and a lot of them are little bitty thumbnail images, but some of them are big full frame images. And one of the initiatives that we're working on right now is with the Wikimedia Foundation, we're working on building a big pipeline of data so that people give their data to DPLA, and then if they want, we can put their data into Wikimedia, and then it becomes part of the Wikimedia ecosystem, and you can, people can find it and put it on Wikipedia pages and stuff like that. So when we were starting this initiative, one of our questions was, well, how many of these big full frame images do we actually have? Do we have enough of them to get started on this project? So that's what we're going to be looking at. The algorithm we're going to be using, it's pretty simple. So our data set is a sample of image metadata from our aggregation, including height and width. We're not using the whole 40 million because that would be insane. I think we're using about like 5,000 actual images that have just been randomly sampled from our collection for the purposes of this demo. And we're going to get the longest edge of the image. So whether height is longer or width is higher, we're going to pick whichever one is bigger, and that's going to be the way that we compare the images to each other is by their longest edge, and then we're going to look at the distribution of the longest edge size. All right, so let's go. Michael, since I don't have my chat box in front of me, if you could copy paste this into the chat so people can reference it, that would be awesome. So everyone, whether you're doing a Databricks demo or whether you're doing a REPL or whether you just want to have this code so that you can look at it later, go to this tiny URL link here, ml-glam-images-demo is the link. And I'm going to actually show you walking through the next couple of steps. So this is the notebook that we're all going to look at and copy here. So up here in the upper right hand corner is the link that says import notebook. So you're going to click that link, and this terrible thing shows up that like you can see through. But the important part is that you want to highlight this link in the middle of the page here and copy it to your clipboard. And then you can go to your Databricks. If you're not logged into your Databricks yet, then go ahead and log in. And I'm just going to walk through this really quickly. It's super easy. Over here where it says Workspace, you're going to click Workspace. You're going to find your email address, wherever it is, or your, whatever your username is. Click the down arrow next to your name. You're going to click Import right here. So again, Workspace, over to your email address, down arrow, and Import. And then you're going to click the URL option and just paste the URL in there and click Import. And I'm not going to do it because I've already done it and I don't want it to get confused, but that's it. That's the final step, is just click Import. And then it should pop up with something that looks like this on your screen, where you have this sort of notebook structure going on. And one of the things you're going to need to do is you're going to need to fire up a cluster so that you can actually execute it. So up here in this, where it says detached right now in this drop-down menu, if you click the down arrow, it should give you something. I think it has like a gray dot and it says something like my cluster. So go ahead, if you can, click on that and see if there's a way to say like start cluster or launch cluster. Mine's already going, so I'm sorry I don't have the inactive state to show you. But so from here, there should be a way for you to start your cluster. It takes a couple minutes for it to start up. And if that isn't working for you, you can also highlight this, sort of navigate to this first cell here and push Shift Enter. And then something like this will pop up that says, hey, do you want to launch a cluster and attach this to a cluster? And I'm going to say yes. And then it should do a little bit of thinking for you while it's getting all of this ready to go. So again, the two steps here, the two options are this drop-down menu up here in the upper left-hand corner should have some sort of an option when you drop it down to get your cluster started, or highlight the first cell and click Shift Enter. All right, so while you guys are doing that, if you get stuck or have questions, put it in the chat. I'm going to quickly show for those of you who are using your REPL what you're going to want to do. Okay, can you guys see that now with my little REPL in the screen? So if you're using your at-home installation, what you want to do is just go to wherever your installation is. So mine is, I have like 12 versions of Spark here. I'm going to use 2.4.6. You can use whatever version of Spark you have downloaded, it's fine. So you just want to do whatever, get to whatever directory you have your Spark in, and you just want to run bin PySpark. So that's the location of your Spark directory /bin/PySpark, and then click Enter, and it should run up some text for you, and then you should get this big thing that says Spark, really big. And if you've got that, then you're ready to go. And from here, all you have to do is copy and paste the commands in this notebook. So you didn't have to do that whole import notebook business. You just need to look at the link to the first notebook that we looked at, and you can just copy and paste commands. I hope that you guys are seeing this, but I'm just copying this first command here and pasting it into my shell, and we're going. There we go. So that's all that you guys need to do to follow along with your REPL. All right, so I'm going to minimize this, and I'm going to go back to here. This is a notebook we're working on. And all right, so let's get going here. So again, we've got millions of images, and we think that some of them are small, but that some of them are large, and we want to find out how many small ones we have and how many big ones we have. So the first thing that we're going to do is we're going to read in a CSV file that has our image dimensions. This is an old version of this. I think it'll still work. You guys will have something different. Oh, shoot. All right, I'm going to close this, and I'm going to quickly do, that's an old version of this notebook. So I'm going to just do what I told you guys to do really fast. My apologies for you having to watch me do this really quickly. Import from URL. Haha, that should be what yours looks like. There we go. Now we're good to go. And I need to attach. So what we're going to do here is we're going to read in this file. I've just put this file up on S3. which, by the way, if you want to take this data home with you, all you need to do is copy this link right here. And if you put it in your browser window or curl or whatever, that will download this file for you onto your local machine so you can take it home. So we're just going to read this in. This bit here is just reading this into the local file system so that then Spark can get it. So it's just pulling it from this web address, reading it into the local file system, and then this input statement, Spark.Rdd option. We're saying header true means that the CSV file has a header line. So it's telling it to interpret the first line of the file as headers for the columns, and then CSV to the file path. So if I do this, you can see it's telling me, oh, look, Spark has a job going. Hey, it read it in. And I can tell that it read it in because it's giving me this output that says that I now have a data frame. Woohoo! So the next one I'm going to do is now input is the name of my data frame. And I'm going to print schema. And that is going to show me the schema of my data frame. So these are all the column names. So you can see that we have the image ID, the provider, which is where we got the image from, and the height and the width. And so now I'm going to look at the first 10 rows, this show command, the data frame.show. I'm going to look at the first 10 rows of my data frame, and you can see it's like a table with the column headers up here and then the values down in here. So you can see the image ID, the name of where we got it from, and then the height and width dimensions. All right, so the next one I'm going to do is I'm going to count how many rows there are in my data frame. So how many images are we working with here? Ah, there we go, 5,000. So that's counted my entire data frame for me. All right, so just to sort of pause for a minute and thinking about what's going on here. So we have this whole table and it is currently distributed across the entire cluster. So as soon as I read this table in, using the command spark.read option, this command right here, it read in this entire CSV file, interpreted it, and it spread it across the cluster. So this is a distributed table of things that we're looking at, and we're able to interact with it as if it's just one thing and not think about the fact that it's distributed. All right, so the next thing I'm going to do is I don't really need all of these columns. I don't need the provider. I don't need the ID. The only thing I'm really interested in is the height and width of this data frame. So this here is going to select the height and width columns, and then I'm going to show the output of that. So height width, I'm making a new data frame. And in the new data frame that I'm making called height width, we only want these two columns. And there it is, height and width. And just to show you, this is the only thing that we're going to do with the SQL interface, but I threw it in here so that we could see it. You can also, if you want to interact with this table using the SQL language, if you're comfortable with that, you can do this where this create or replace temp view is saying, give me a SQL version of this table that I can interact with. And then you can just go spark.sql and type in any SQL command that you want and do it. So here I've done the SQL command for doing the same thing, get the height and the width columns from the table, and then show it. And there it is, same thing, height and width columns. All right, and now I'm going to print the schema of my height and width, which seems obvious. We've done that before. We know that there's a height and width table, but the thing to look at here is that these are currently being interpreted as string values. And if we're going to get the biggest one, then we need to look at them as integer values instead. So I'm going to import some libraries that are good for for data processing. And I'm going to do a cast. So I'm going to cast the values, the height and width values from integers into strings. Or no, sorry, the other way around, from strings into integers. So that's what this is going to do. I'm going to say, all right, I'm going to make a new table, a new data frame called dimensions. And I'm going to select the height, but I want to make it an integer type. And then I'm going to select the width, but I'm going to cast it to an integer type. So we're going to do that and then print our schema again. Where did you go? There we go. And you can see it's changed it. So now we have a table, a data frame called dimensions, and we have the height and width, but they're now in integer formats. All right, so now we're getting to what we want to do here. we want to find the longest edge. So which one's bigger, the height or the width? And Spark actually has a lot of really nice built-in functionality to do these sorts of like querying your data tasks. So they actually have a built-in function called greatest, and you can give it 2 columns and say, tell me which one's bigger. So we're going to create a new data frame called with longest. And we're going to say this data frame is going to have a column in it called longest edge. And the value of that column is going to be whatever the biggest value is between height and width for each row. So I'm going to do that and show. So now we have our new data frame, and it has a height and width, and then we can verify longest edge. You can sort of run down the list here and verify that, yep, it's pulling out whichever one of these 2 integers is the biggest in every row. All right, so now we're ready to look at our distribution. If we want to just look at the raw numbers, there's this function called describe that you can do on any on a data frame, on a numeric value data frame column. So we're going to say select this longest edge column, describe it, and then show me the results. And you can see that it's given me the count. So we've seen this before. This is how many rows are on the table. And it's given me the mean, the standard deviation, the min, and the max. So the smallest edge we have is 75 pixels, and the biggest one we have is 2000 pixels. And the mean, the average, is 374. And that's kind of helpful, but it's not really a full distribution. So now what I'm going to do, this is the exciting part, is we're going to do a visualization of this data. And for those of you who are doing the REPL, this is the only thing that you can't do on the REPL. So just sit back and watch this part. The REPL does not do, obviously does not do fancy big data visualizations like this. So anyway, and this is a way that you can also see how this can be integrated. So I'm going to import Matplotlib, Pandas, NumPy, and get into some visualization territory here. And I will admit that visualization is not my strong suit. So this is a pretty simple visualization here. We're just going to build a histogram. And we're going to look at the longest edge value, and we're going to plot out a histogram, which is going to show us the distribution. So I'm just going to, with no further ado, hit return. It's going to process it for a second and then pop it up for me. So there's my histogram of image sizes. So on the vertical axis, you can see the number of images, and on the horizontal image, I've just sort of bucketed these. So this is longest edge from 0 to 250 pixels. The next bar is longest edge from 250 to 500. So you can see we have a whole lot of data in this small, a whole lot of images in this small data range, which is what we were expecting. But then over here on the right, you can see, well, there's, there's what, maybe 100 images in our sample of 5,000 that are actually like pretty big images. So that tells us that, we don't have a lot of really big images, but, we maybe have enough images, enough big images to do something with, or to start doing something with. So that's it. That's the end of this particular code demonstration. So I'm gonna stop sharing, and you can feel free now that you have this this notebook. I should have said this from the beginning. Now that you have this notebook loaded into your own workspace, it's yours. It's your copy of it. You can do whatever you want to. So as we're coding along, or if you want to come back later and do it, if you want to experiment with like typing different stuff in and trying different things, feel free to go ahead and do that. It's your copy now. You can do what you want with it. All right. So now I'm going to go back to our slide deck, and we are at another checkpoint. So I'm actually not going to make my screen big. I'm going to go ahead and stop sharing because Michael is going to take over and do the next section. But in the meantime, does anybody have any questions? Feel free to type in the chat or raise your hand.
Olga, did my explanation make sense? Is that, I think the overall idea here is we're trying to show something basic to get people familiar with loading data into Spark and working with some of the data frame APIs. And this was, a real world problem that we had where we had some full frame images mixed in with our thumbnails, and we wanted to see, what the distribution or percentage of our data or thumbnail data that actually had full frame images that might be targets to upload to Wikimedia. So this is actually something we had to do at one point across, I think at that time it was something like 28 million rows.
Mm-hmm. Yeah.
Okay, so I will move on to the next section. And I'm just going to kind of talk about the architecture of Spark and how it works behind the scenes of those APIs and data structures that we talked about earlier. I think sometimes the best way to understand why something is designed the way it is to think about it what it was designed to fix. For example, Perl was designed to fill the void between low-level C code and shell scripts, and Java was meant to be a better C++ for certain applications. Spark was designed to be a Hadoop successor in many ways and solve some problems that Hadoop wasn't built to. To be sort of glib, Hadoop was designed to be a compute engine that maximized the throughput of spinning hard disks, but we have a lot more RAM available than we did in 2006 now, and we have new types of problems. Machine learning and more complex data analysis has become a really big industry and a big problem for a lot of different types of institutions. So in many ways, you can think about Spark as the answer to some of the drawbacks of the abstractions that Hadoop and MapReduce bring to the table, including better ways of thinking about maximizing the use of hardware in I/O, scheduling work, working with storage, and in particular, how to deal with making iterative algorithms performant. And that last key point is a key advantage for Spark when doing some types of machine learning work versus Hadoop. Lastly, Spark comes with much higher level built-in APIs, which are a real boon to developer productivity and ecosystem accessibility. It's much harder to write raw Hadoop code than it is to write raw Spark code. Originally, I called this slide Hadoop killer, but that elephant is just too darn cute. I love it. So I'm going to take a second to talk about how Spark runs code, which will give insight that not only will help you understand how Spark works behind the scenes, but will also help you understand how to write code for it effectively. In Spark, nothing is modified in place. Every operation that changes data, and I put quotes around that, does so by making another RDD or data frame with the changes applied. We can go back to different versions of the data and compute other new versions of them with different changes. So we can kind of branch from a given save point, call it. And when it's time to save the data out and export it, Spark won't even let you overwrite your old data. You'll need to write it to a new location. So really, immutability is a key concept here. New data frames are calculated not when you describe how to create them, which are operations called transformations, but when you ask for them to be sent somewhere, which are called actions. So in using the example that Audrey just brought up, a select statement on a data frame doesn't actually run any code. It just, if you hit enter on a select statement, Spark will just return immediately, even if you have like petabytes of data behind that select statement. And what's happening is Spark's kind of building up the record of what you want done. So laziness lets Spark optimize storage so it can decide to hang on to multiple copies of the data with different transformations or build them on the fly if necessary. That's why if you're coding in Spark's REPL or in a notebook, some operations will return instantaneously when they should take some time to compute. Spark's just building up a series of steps it will take and will only execute them when you perform actions. So it ensures that it plans out the execution efficiently. Finally, parallel is the keyword of this slide. Spark's APIs and architecture enforce a shared nothing model that makes your code extremely parallelizable, which means your code can be easily reused in context with more data and more infrastructure without rewriting anything. So when we say parallel and shared nothing, that means you can't have a variable that you're incrementing in a loop inside of one of your operations. It'll disappear by the time it gets to your next row. There's specific APIs for doing things like running counters and things that work maybe slightly non-intuitively, but when you conform to these APIs, your code becomes a lot more parallelizable and scalable. One thing to mention here is the concept of splittability. To get Spark to be able to schedule parallel workers across all your data, it needs to have some visibility into where the record boundaries are in your data so it can distribute tasks to chunks of it. That means in practice, Spark has some sensitivities to the format of your data that you should be aware of. For example, a 1 terabyte CSV file is very splittable, since Spark can look for new lines in the file to figure out how to split it up. A 1 terabyte Java array, or sorry, I meant JSON there. JSON array isn't very splittable because you'd need to parse the whole thing to find out where the records are. But that same array translated into the JSON lines format, where one JSON object appears on every line of the file, is very splittable. Any questions on splittability there? Okay. Now I'm going to quickly talk about the runtime, the world that your code executes in. Yeah, I'm going to touch on that in a second. It doesn't actually read the file in memory to find out where to split. It kind of takes a rough guess about, like, if you have 4 nodes running, it will take rough guesses about where a record might terminate within like each fourth of that file, and scan through to find the actual byte that the line ends. And then it'll tell a node, all right, your chunk is bytes 0 through 5,768,000, and then that node will go find that data. So what that means is the individual nodes are loading the data in parallel. So if you're working with something like Amazon S3 or something where you can load a lot of data in parallel across several nodes, that work of the data load is actually spread out along the cluster too. So that's kind of a rough idea what splittability gets you. It means that it doesn't have to like sleuth through the whole file and decide who gets what. So most code that executes in Spark is running in a Java virtual machine. That means that a lot of the runtime is heavily performance tuned, in the sense that it's making use of the work that's been put into the Java virtual machine over the last several decades. And also that you have a lot of access to a lot of libraries written for the Java ecosystem, in many cases, even if you're writing in Python or R. In many data frame API calls, you might be describing to the system the operations you want to do in what looks like plain old Python or R, but under the covers, the Spark runtime is translating that into custom code that never runs Python or R. Exception for that is RDDs. You can think about that in the same way that you think about how databases execute SQL. The SQL is a high-level language that tells the database what you want to get back, but the actual code that executes uses an execution plan that looks nothing like the SQL that the database generated. I'm going to talk about speed quickly here. This is kind of an artifact from our original experimentations with using Spark to do some work that we were trying to do with something that was a lot slower. And the executive summary here is that our original Ruby REST implementation over a triple store took 90 hours or so to do something, which was mapping a data set from the data that came into our internal DPLA format. And I believe that data was JSON, if I'm not mistaken. Getting rid of the triple store and using local storage knocked that down to 8 hours and 44 minutes. Doing the same work in a Python multi-process implementation, which the Ruby implementation I think was single-threaded, knocked it down to 17 minutes. A standalone Scala implementation took 2 minutes and 19 seconds. Doing that same code in Java with the same libraries essentially knocked it down to 1 minute and 40 seconds. But in a surprise finish, running the Scala code in Spark was fastest at 41 seconds. Which, when you think about it, that's a little weird, right? It's Scala either way, same libraries, but there are some reasons for that. Here's some examples of the tricks that Spark does to make sure your code runs as quickly as possible. Spark tries to run with all the data in memory to avoid I/O. It can spill portions of your data set to disk if you're out of RAM, so it can kind of dynamically manage that for you. It transparently uses data compression. So if your data is in a compressed format, like I'm trying to think of one that's splittable. Well, Parque is compressed. So Spark will transparently decompress that data and work on it for you, which improves I/O throughput. I think in DPLA's case, we have plain JSON exports of our data that take up, I want to say 60 something gigabytes, and then The Parquet version of that will be something around 11 gigabytes or something like that, and it's actually faster to use, even though you would imagine that the decompression uses CPU. But in IO-bound cases, that compression is actually free because your CPU would be stalled otherwise. So it's kind of free performance there. Memory management tricks to avoid object generation in the garbage collector. So like I said, when Spark is kind of generating that execution plan, rather than thinking about it in an object-oriented way where it's taking the bytes that are in your data and instantiating objects and performing operations on those objects and then throwing the objects away and freeing the memory, Spark can just memory map that data, change the execution plan that you specify into code that works on that binary data without instantiating any objects, and then write binary, write it back out. So it's performing some tricks under the hood there. And that's something that only happens when you're using the data frame or data set APIs. So the takeaway here is that they're solving performance problems in ways that you'll never be able to, because you probably don't have the resources to devote to that. You should probably just borrow what they're doing. Quickly, I am going to touch on the cluster architecture. And this is the Spark project's diagram of how a cluster setup works. If you run Spark on a single machine, some of this complexity goes away, but the programmatic API stays the same. So you can see here that your code gets initiated into something called the driver program, which creates an object called the Spark context to talk to the cluster. And the cluster manager is responsible for distributing work to the worker nodes, ensuring that they're still alive and doing work, and redistributing the work when they drop out of the cluster. And the worker nodes each contain data and job tasks that define units of work that are running, and sometimes exchange data between each other to make the various stages of the job work. So you can imagine if you're doing something like a join or a sort, that the nodes would have to shuffle the data between them to make it sit in the right place. And that's how this happens. It's inter-node communication, and it doesn't actually necessarily need to touch the cluster manager. Okay. We are at another checkpoint. Does anybody have any questions or comments for that section? Okay, hearing none, we worked a break time into this. So if anybody wants to get a beverage or use the bathroom quickly, I think we would reconvene in 10 minutes.
Please do come back, because at the second half of this, we're really going to start getting into some machine learning stuff. The first half was getting up and running and understanding Spark and the APIs and how to do basic codes. The second half is really digging into some data mining and machine learning applications. So it should be fun, and I hope that you all will come back in 10 minutes to join us. All right, so we're going to do another code demo, and this time the things that we're going to be focusing on are looking at the Rdd abstraction, the resilient distributed data type, which is that low-level data type, which is useful in some cases still. I think it's good to know what it is and how to use it, even though most of the time you'll probably be actually using data frames. We're also going to look at a big data application. So a reason why Spark shines is because it can handle big data problems. And we're going to be looking at the cluster architecture in a little bit more detail, well, not really detail. We're going to be doing coding that requires us to think about the cluster architecture. And we're also going to see the lazy execution in action. All right, so the case study we're looking at this time is, as you know, we have millions of metadata records. And one of the things that we've been thinking about recently is the impact that having near duplicate records. So we can catch in our regular ingest processes, we can catch records that are exact duplicates. That's a pretty easy thing to find. So we weed out exact duplicates from our collection, but we also have a lot of near duplicate records. I'm sure that you know, in a large archival collection, for example, if you have photograph after photograph after photograph of almost the same thing, chances are that the metadata records are going to be very, very similar as well. So we're thinking about how having lots of near duplicate records might have an impact on things like search engine optimization and our discovery systems. So what we wanted to find out is how many of our records would qualify as being near duplicates. And for this example, we're going to be looking at the collection from the New York State Military Museum. So I just wanted to highlight them real quick because they have a neat collection. This is one example of a thing that they have, which is a photograph of a Civil War soldier. So this is the data that we're going to be working with. They have a lot of enlistment records, photographs, things like that about the history of New York State military. All right, so the algorithm that we're going to be looking at, we're going to take a sample of item descriptions from the New York State Military Museum. We're just to simplify things, we're just going to look at the item description. So we're not going to look at the subjects or the titles or the any other information about it. We're just going to look at the description field. And we're going to turn each document into a set of shingles, calculate the Jacquard similarity for each pair of shingles, and then set a threshold and say if the Jacquard similarity is above some threshold, we're going to consider it a near duplicate. And if you don't know what these words, shingles and Jacquard similarity mean, then I'm going to tell you right now. All right, so shingles. This is a common way to represent a piece of text as a set so that you can run computations on it. And a quick definition, a k-shingle is any string of length k that's found within a text document. So if a description 1, we had a photo of pig, we would break that down into shingles by running through and saying what are all of the possible combinations of 5 characters stuck together. So we start with photo, that's 5 letters, and then we move over 1 and go hoto plus a space. And then we move over and go O-to-O and get the next one. So you can see all the way down the line, those are the 5 shingles that represent photo of pig. And if we have a very similar piece of text, like a photo of pie, you get a lot of exactly the same shingles, but at the end, you can see that some of them are different. So these 2 descriptions, photo of pig and photo of pie, have 7 out of 9 shingles in common. And the Jacquard similarity is a way to measure a similarity of sets. The mathematical definition is the ratio of the size of the intersection to the size of the union. If this is our space here, we have 8 total items between these 2 classifications. And you can see that of the 8 possible dots here, they share 3 of them in common. So their Jacquard similarity is 3 out of 8. And this near duplicate detection is kind of a classic big data problem. And we can see why. So the first issue is the size of the data. You can see it if we take our description photo of pig, that's 13 characters. And if we blow it up into shingles, then all of a sudden we have 45 characters. So we've just multiplied our data by almost 5. In order to create shingles. So if you imagine you're starting with a very large data set and then you create shingles, suddenly you have multiple times as much data as you had before. So that's the first part of it being a big data problem, is that you're dealing with a lot of data. The second part is that in order to find documents that are similar to each other, you have to compare every document to every single other document. And so I think we're looking at a sample of 1,000 documents. And in order to get the similarities for 1,000 documents, you have to make almost 500,000 comparisons. And just to sort of put some, to think about large numbers, I think it's good to give an example. So say we had a good computer and we could do 1,000 comparisons per second. That would still take us over 8 minutes to look at just 1,000 documents. And so you can imagine that this is a problem that grows exponentially. So once you get into having not 1,000 documents, but 1 million or 1 billion documents, then it just blows up. The computation time just blows up so huge that it becomes unwieldy to do. And if you're thinking, well, you don't actually have to, those of you who are good data scientists in the room are probably thinking, well, you don't actually have to compare every single document to every single other document because there's ways to estimate that. And if you wanted to do something like a locality sensitive hashing algorithm, Spark MLlib does have tools for that. They have libraries for that built in. We're not going to do that today just because I want to keep it simple for those of us in the room who aren't data scientists already. So we're not going to look at that kind of stuff. We're just going to brute force it and actually compare every document to every other document. Okay, so in order to do this in a cluster, there's a lot of ways to do this. using a cluster, but we're going with a pretty simple method here. So if you look over at this first diagram, the gray block on top represents the master node. That's the driver that's controlling everything. And then the 3 blocks underneath are worker nodes. And these 3 different colored, the pink, yellow, and blue squares here inside the blocks represent the data. So this is going to be our description data. And when we first read it in, it's going to be really helpful and distribute it for us across these worker clusters. And then we're going to say, okay, now we need to compare everything to everything else. We need to compare all the pinks to the yellows and the pinks to the blues and the yellows to the blues. But of course, these worker nodes are all sort of independently running, and they don't know what's on each other's machines. That's part of the design of the cluster. So how do we get it so that each one of these worker nodes can actually have all the data that it needs in order to be able to run these comparisons? So what we're going to do is we're going to run collect. It's actually a function called collect. We're going to collect a copy of the data up to the master node and join it together as one data set. And then we're going to broadcast a copy of the data down to each of the nodes, so that then this pink block here will have access to the full data set, and it can run its section of the comparisons. And the yellow block can run its section of the comparison, so compare the yellow blocks to all the rest of the data. And then this blue one can compare its little blue section to all the rest of the data. This isn't probably like the most efficient method that you could use, but it's a method, it's a simple method, and it's the one that we're going to do because it demonstrates the concepts of thinking about where your data is on the cluster and how to give each worker node all of the information that it needs in order to be able to perform its task. Okay, so the next, it's time to go to the next notebook. So this is a new tiny URL here that you guys can go to in order to pull down the notebook. And then all the directions are going to be just the same after that. So I'm going to copy this. Okay, here we go. Again, you're going to come to this notebook. You're going to go up here to the upper right-hand corner and click Import Notebook. You're going to get the URL. And then I'm going to go to my Databricks workspace, import, click URL, paste in the new link, and import it. And here we are. And then I need to attach my node, which is probably still running from the last time that you guys did this. So probably you have a green dot, but if not, that's fine. Just start it up again. And we're ready to go. All right, so the first thing that we want to do is define, we're going to do our shingling first. So we're going to, I haven't actually read the data in. I'm just going to define these methods to make sure that we have the methods that we need in order to do the shingling and the Jacquard similarity. So this is just a Python method that is going to make shingles. And I've defined my shingles here as 5. So we're going to make 5 shingles. And my function here is going to take a string called my string, and it's going to return all of the shingles. So I'm just going to run this really quick to make sure that it's working. So I'm giving it the string I love libraries, and I'm going to check and make sure that the shingles look right. And they do. So you can see that this string I love libraries has been broken down into 5 shingles. All right, so we've got that. We've got a definition, a function to make shingles, check. Next, we're going to have a definition that's going to do our Jacquard similarity for us. You can sort of read through the internal logic here. You're just getting 2 sets. You're doing the union of the set, the intersection of the set, and then finding their ratio and returning it. And so just to test that I have written this function correctly, we've got 2 sets here. We're going to start with set 1 and set 2, which you can see are identical. They have identical shingles. So you would expect that the Jacquard similarity would be 1, because all of the union and the intersection are the same. And that's correct. They have 100% of their shingles in common. So you expect the Jacquard similarity to be 1. All right, and now we're going to move to the next one. We have a new set of shingles here, the same one for set 1 and then set 3. You can see that it has some different shingles. So these ones have 1 out of 5 shingles in common. So you would expect that the Jacquard similarity would reflect that, and it does, 20%. It's the same as 1/5. Okay, and then lastly, the Jacquard similarity of two sets that are completely different. They have no shingles in common. So you would expect that the Jacquard similarity would be 0 because they have nothing in common. And that's correct. All right, so we have our shingles method. We have our Jacquard similarity method. Now it's time to work with our whole data set. All right, so this time we're reading in a text file. Last time it was a CSV file. Again, if you want to grab this data from S3 and keep it so that you can work with it on your own, you can just go to this link here and you can just download this data file. So again, we're going to read this in input, and this time we're going to read this sc.text file. Sc is the Spark context, by the way. Michael mentioned that. So the Spark context, read in a text file, and this time this command is going to read it in as an RDD. So last time we read in our text file as a data frame. This time we're reading it in as an RDD, and it is going to automatically distribute that RDD across the cluster for us. And then this line input.first is just going to pull back the first value from the RDD and display it so that we can see what the data looks like. And you can see right here, oops, you can see right here, this line is the description. So this is the first description of one of the items from the military museum's collection. And the rest of them are, similar text strings like that. Okay, so I want to know how many are we dealing with here? So I'm going to do a count on my RDD. And you can see the count method is the same as the one that works on the data frame. There's a lot of shared methods between the two things. So I counted my RDD and there are 1,000 item descriptions. So that's how many we're working with this sample. And then we're going to try turning each one into a set of shingles. That's our first step. So I'm going to do a Lambda function. Lambda functions are really useful when you're doing any kind of functional programming and working with Spark. It's a nice way to iterate through your RDDs. So if you start using Spark a lot, you might find yourself using a lot of Lambda functions. So what the Lambda function does, if you've not seen a Lambda function before, it's going to basically you define an anonymous function. So you tell it what you want it to do here, and you don't have to give it a name. It's an anonymous function. So I feel like I'm not explaining this well. Let me back up a second. What this line of code is doing is input is our RDD. The map is going to say, okay, we're going to run through every single element in the RDD, and we're going to do something to every element. And what we're going to do is that we're going to, we're naming every element a description, because that's, for us to understand that's what it is. So every line is a description. And then for every description, we're going to run this command, which is our definition our function that we defined in order to make a shingle. Okay, so I'm just gonna print this, and you can see that our single line of text, which was this formal portrait of soldier, et cetera, has now been turned into a shingle. And you can see that it's a lot bigger. It's a lot bigger than the single string of text. There's a lot more data here. So this now has, this has happened to every single one of our descriptions has now been turned into a shingle. Okay, but now we're in, if you can think back to that diagram of the data being distributed across the nodes, each node has one little portion of the shingles, but they need to be able to compare them to everybody else. So we need to pull all the shingles together and make a master data set that we can then distribute to all of the nodes. So this is how we're going to do that with the broadcast and collect. So shingles collect is going to say, okay, pull all of the shingles to the master node and then broadcast that, a copy of it out to every single node. So I'm going to run that, and it doesn't really give us any data back, except it says that Spark completed a job. So now every single node has a copy of the full set of shingles, and it can run its comparisons. All right, so we're going to define one more function here. First, I'm going to set my threshold. So I'm going to set my Jacquard similarity threshold at 0.9, which is pretty high. So we're looking for very close duplicates here. There's no hard and fast rule as to what the Jacquard similarity has to be. It just depends on your use case. Okay, and then I want to be able to compare, each node is going to look in turn at every single shingle set that it is responsible for and compare it to everybody else. So that's what this method is going to do. It's going to say, you know, take your current shingle, the one that you're working with. You're going to compare it to every single shingle in this broadcast shingles collection that you have. You're going to find the Jacquard similarity. If the Jacquard similarity is above our threshold, which is 0.9, then you say, hey, I've found a near duplicate. And then I went ahead and just said, if you found a duplicate, if you found a near duplicate, then go ahead and break the loop so that we don't have to keep comparing. It just cuts down on the number of computations we have to do. And if you'll notice here, I initialized this near duplicate as -1. And the reason I did that is because every shingle is going to see itself at some point, and that is definitely going to be that's going to be an exact duplicate. So we want to initialize our count of near duplicates at -1, so that when it sees itself, it goes to 0, and then if it sees another one, then it'll actually go to a positive number. There are other ways that you could deal with that, but this was the one that I chose. All right, and then in order to actually run this, it's pretty simple. We're going to do another lambda function here, and we're just going to say for every shingle set, I want you to run this method to see if it has a near duplicate, and the has near duplicate will return true if it finds a near duplicate, and it will return false if it doesn't. And then I'm going to filter and just get all of the true statements. So let's run this big computation. And here, I'm going to pause for a moment, and I'm going to ask you how long you think it's going to take to run this giant computation. And the answer is, oh my gosh, it only took 0.07 seconds. But it was a trick question, because if you'll remember the lazy loading property of Spark, it actually hasn't run this yet, because map and filter are not actions, they are transformations. So all that we've done is given Spark a map of what we want it to do at some point. So it hasn't actually run the full set of comparisons yet. So now we're going to try and actually run it. I'm going to take this near duplicates, and I'm going to run the count on it. And count is an action, so that's going to force it to actually evaluate. So we're going to run it, see how long it takes, and then see how many near duplicates we found. So you can see it's thinking, it's running these millions of computations that it has to run. And we'll just see how long it takes to run somewhere around 500,000 comparisons. There we go. It took 17.68 seconds to run all of those comparisons. And we found 147 near duplicates. So out of 1,000 records, record descriptions, we had 147 that had the Jacquard similarity greater than 0.9. Okay, so that was our second code demo. Did we get any questions, Michael? I closed my chat window.
No, we did not.
Okay, great. So let's move on to Spark ML, which I think is why you might all be here, to learn about the machine learning library, which is super fun. So the Spark ML library includes a bunch of stuff. It has, of course, some ML algorithms, including things like classification, regression, and clustering. It has featureization tooling so that you can do things like feature extraction and dimensionality reduction. It has this concept of pipelines, which basically lets you combine a bunch of different algorithms together into a single workflow. And that can be convenient when you are doing something that you want to run over and over again, maybe with trying out different hyperparameters. It's nice to have the pipeline concept. It's just kind of makes the coding easier to work with a pipeline. It has some evaluation tools. So metrics, different metrics to assess your ML algorithms. So if you wanted to do, what is that one called? Where you're looking for true positives and false positives and true negatives and things like that. It has those kinds of evaluation tools. I mean, different algorithms have different tools, so there's some available for you. It also has, this is pretty nice, it has the ability to persist your actual models. So if you train a model on a data set, then you can save that model and persist it forever. And so you don't have to, worry about retraining in order to get the data again. So you can save a trained model and then save it, and then you can, apply it to a different data set or share it with somebody else or whatever you want to do. And it has some utilities built in for things like linear algebra, statistics, blah, blah, blah. So it's pretty full featured. And in terms of the machine learning algorithms, I mean, there's so many of them. I looked at the documentation and I was like, oh, maybe I'll pull out some interesting ones, but there's just so many different algorithms that it has going on there. It groups them into the feature extractors, transformers, and selectors, classification and regression, clustering, collaborative filtering, and frequent pattern mining. But I mean, I would encourage you to just go and look at the MLlib documentation and see what they have there, because there's a lot of different algorithms and variations on algorithms that you can use. So pipelines, I'm going to quickly run through this. I think it's a lot easier to see it in action than to talk about it abstractly, but just to put the definitions out there, pipelines use the data frame API as their main API. They do have an RDD, an RDD API, but it's depreciated now. I think it's still supported, but they're trying to get everybody to move over to the data frame API. So it has this concept of a transformer, which transforms a data frame into another data frame, an estimator, which produces a transformer by fitting or training data on a data frame. So you do your training, and the estimator is basically instructions on how to apply that model to a set of data. And then the pipeline is chaining multiple transformations and estimators together. All right, so I'm just going to jump right into the code demo on this one. And what we're seeing in action is really just the Spark ML library. That's the focus on this one. So our case study is if you have a very large collection, you might not have a complete understanding of everything that is in that collection, especially for we're just metadata aggregators. We're not really involved in things like collection development and hands-on interactions with the collections. So this question of what's actually in our collection is kind of a big one for us, but it can also be interesting just to people have done this in libraries to build. They've used topic modeling to build new discovery tools, new discovery interfaces for their users. They've used it to sort of help curators to understand what sorts of topics might be good to do exhibitions about. They've done it to figure out some things that they have that are sort of distinctive and special so that they can talk to their stakeholders about, why their institution is special, what their institution is contributing to the world. So there's a lot of reasons why you might want to be able to pull out major themes in your collection. And we're going to do another collection spotlight. We're not going to use the whole of DPLA for this, but we are going to look at the Newberry Library in Chicago, which is a great independent library. And it just so happens to have a really large collection of stuff about trains. You can imagine Chicago was a big railroad hub, and it has a lot about railroad history, which I think is pretty cool. It has other stuff too, but that's one of my favorite things that they have. Okay, so our algorithm for this one, the data set we're going to look at is we're just going to look at all of the Newberry Library this time. We're going to pull in their whole data set, and we're going to look at the titles and subjects and descriptions of each item. I picked title, subject, and description because those tend to have the words that describe what an item is about. And if we're looking at aboutness, it seemed like a pretty good fit. We're going to take these titles, subjects, and description texts, and we're going to turn them into a bag of words. Represent each bag of words as a sparse vector, and then train an LDA cluster to find underlying topics. And again, I'm going to go through what each of these bolded words mean if you're not already familiar with them. So a bag of words is a way to represent a document as a multiset. A multiset is an unordered collection of words in which you can have repetition. So that's what distinguishes a multiset from a set. And the first step is to transform words into word token. And a word token is, I think a formal definition is a semantic unit that's useful for computer processing. But it's basically just a way of sort of normalizing a word. So you do things like, strip out punctuation and capital letters so that it's easier to match words with each other without a bunch of extra useless semantic information attached to it. And you also often remove stop words, which are common words that don't have a lot of semantic value. In the English language, the words like and the that appear all of the time, but that aren't really meaningful for things like trying to understand topics. So for an example, if you had a document like this, a train engine, a passenger car, and a coal car, in order to pull out the word tokens, you would get train, engine, passenger car, coal, and car. You see car is in here twice. And things like commas have been stripped away, stop words have been stripped away, and it's all lowercase. And then vector representation is, I'm just going to go through, I feel like the best way to do this is to just do an example. And so you can kind of get the gist of it. It's just, again, it's a way of representing this data in an efficient way that a computer can understand. So we have our bag of word tokens here, car, coal, train. Oh wait, that's not right. This is not the bag of words. Say we have, in our entire collection, these 6 words are the only words that appear in the entire collection. I mean, obviously that's kind of a silly example. You would never expect a vocabulary to be only 6 words, but there's a limited amount of room on this slide. So I just said we have a vocabulary that contains only 6 words. And these are the words, 1, 2, 3, 4, 5, 6, 7. There's 7 words here. There are 7 words in this vocabulary. And then you can identify, if you have this in like an array, you can identify each word just by its index in that array. So car is 0 because it's at position 0, coal is 1, train is 2, engine is 3. And then suddenly you have a lot less data that you need to represent this because each of these words can now just be represented as a single integer. So now we have our bag of words from the previous example. So our photo of the train and the train engine and the coal car and the passenger car was reduced down to this bag of words. And it's represented as a sparse vector in this way. So 7, because there's 7 words in the vocabulary. The first array here is telling you the positions of all of the words, or the identifiers of all of the words that exist. So you can see we have 0 because the word car is there. We have 1 because the word coal is there. We have 2 because the word train is there. The word engine is not in our bag of, oh, it is in our bag of words. No, I did it wrong. It should say 3 here because that's the word engine.
This is why you should run your machine learning on Spark clusters and not Audrey. Yes,
exactly. Audrey is bad at machine learning by hand. Just ask my professors. But anyway, this next array here is telling you how many of each word you have. So at least this first one is right. Yeah. So the word car appears twice. And so we have a 2 here to indicate that this word appears 2 times. All right, we're just going to move on. So the LDA, latent Dirichlet allocation. I'm sorry if I'm saying Dirichlet wrong. I feel like I get it wrong almost every time I say it. This is a clustering model. It's a form of unsupervised learning, which means that there's no right answers. We don't know ahead of time what we're trying to predict. We're just trying to pull out a new pattern that we haven't seen before. And it assumes, the intuition is it assumes that there are hidden topics that describe the contents of a collection, and it's going to discover these topics by doing a statistical analysis of word vectors, which we just saw that I produced incorrectly. And then you can look at a topic, you can sort of understand, a human can understand what a topic is by looking at the words that are the most strongly associated with that topic. All right, so we're going to code again. Here's our link to our last notebook. Here we go. This is our LDA. Again, I'm going to import the notebook by copying this link. I'm going to go workspace, my email address, import, URL, and put the link in. And I'm going to attach my cluster. All right, so here we are. The first thing we're going to do is we're working with the CSV file again, and we're going to read it in as a data frame and show the first 10 lines. And this is exactly what we saw in the first demo. But we're going to see what this data looks like. There we go. All right, so you can see this is what we've got going on here. We have a description column that's got some descriptions in it, some are missing. Subject column, again, some subject terms and some are missing. And then the title of the collection. And I want to know how many things we're working with here. 13,248. So that's exciting. This is our biggest data set of the day. And it's right there in case you didn't see it. 13,248 records. And so now we have this broken up into these 3 different columns. And in order to form my bag of words, the first thing I want to do is just pull all of those strings together into a single string. So to do that, I'm importing some of our functions here that's going to let me do things like concatenate. And I'm going to create a new data frame. I'm going to, this concat WS means concatenate with a separator. I'm defining my separator as just a simple space. And the 3 columns I want to combine are title, subject, and description. And I'm going to call my new column metadata. And I'm just going to show the first 2 records because it's going to be big. And this false here means you see in this one, it sort of cuts it off after a while and just gives it an ellipsis. If I put false here in my show statement, it's saying, don't cut it off and give me an ellipsis. I want to see the whole thing. So I'm going to do that. And you can see we have 2 of our new columns that are the title, subject, and description all smashed together. And this one, pay attention to this one because this one is nice for seeing how the value changes as we do all of our different transformations. So right now you can see US foreign service trip, blah, blah, blah. There's punctuation marks, there's capital letters. We have some parentheses going on. So we'll see how all of that changes when we make our bag of words. All right, so the first step, we're going to tokenize. And that is, we're going to remove our non-word characters and downcase everything. And now we have our first example of importing the Spark ML library and using some of their stuff. So we're going to import their tokenizer library here. And we're going to say, I'm going to build a regex tokenizer, regular expression tokenizer. My input column is metadata. My output column, we're going to call words. And the pattern that I'm matching on here, this is a regular expression that's saying, give me only word characters, however Python just decides what a word character is. Or I guess how Spark decides what a word character is. Okay, so then I'm going to do tokenized is going to be the name of my new data frame. I'm going to take this tokenizer and I'm going to transform metadata data frame, which was the one that we had just created. This one, this is metadata df. And so we're going to transform it. And then I'm going to select the word column and show so we can see what happened when we tokenized. All right, so you can see now, if you compare these, I don't know if I can get them both on the screen. I can't. This used to be capital U dot capital S for US, and now you can see it's a lowercase u and a lowercase s. Over here, these dates used to be in parentheses, and it stripped the parentheses out, and everything is now lowercase. So you can see what it's done here, but we still have stop words in here, like to, and so we want to get rid of those. So the next thing I'm going to do, I'm going to import another Spark ML feature, which is the stop words remover. And for this one, I'm just using their, the default stop words are English language stop words. If you want to do other language stop words, you can actually define any stop words collection that you want. So you can make an array or a collection or a list of all of the stop words that you want to remove. You can import it from something like NLTK if you want to, and you can just pass any list of stop words, custom list of stop words to stop words remover here. I was going to do it, but I couldn't come up with a way to do it that was efficient to show you guys because it involved like installing NLTK. So, but just so you know, you can do it in languages other than English, but the default is going to remove English language stop words. And then again, we're going to run a transformation. So we're going to create a new data frame called filtered, and we're going to transform it with our remover transformation or remover model here. So here we go. We're going to look at it again, and hey, it's removed all of the stop words. To is gone, and is gone. I think this is funny. The single character S is gone because apparently that counts as a stop word, but U remains because U doesn't. So I'm not quite sure what's going on there, but it kind of made me laugh when I saw it. All right, so then we're going to put everything into vectors. So again, we're importing a count vectorizer feature from the machine learning library. And we're going to transform our bag of words into vectors. Oh, but first, we're going to pull out a vocabulary. That's what I get for not reading my own code. The first thing I wanted to do was, you know, just show you guys that this count vectorizer model is pulling out the vocabulary. So these are all of the words that are occurring in our collection. And I did pass it this optional parameter here saying that if a word doesn't occur in at least 2 records, then just ignore it. I mean, because we're clustering, we're trying to find document similarity. Those single words hanging out there, that's a lot of extra data that's probably not going to add a lot of meaning to our model. So I pulled that out. But you can see that this was pretty easy to have this count vectorizer come in and make a vocabulary of all of the words that occur in our collection. And this is just the first 100 words. There's it's several thousand words in the collection, but for the sake of space, we're just showing the first 100 words. And then if you want to know how long is our vocabulary, 12,029 words. So there's our vector is 12,029 long because that's how many words we have. All right, so now we're going to actually do this transformation of turning all of our rows into vectors. So here it is. This is that first line of data. Here's our one that we've been looking at, our US blah, blah, blah data. And you can see it's quite long because there's more words in it. This one is shorter because there's fewer words in it. And those are our vector representations. So, I mean, I think this is one of the things that I think is fun about machine learning is that we've taken something that was like several sentences of human comprehensible language, and we've just turned it into this like big row of numbers so that we can feed it into a computer and do cool stuff with it. So let's do it. Let's do cool stuff with it. For the grand finale here, we're going to train our LDA model. Again, we're going to just import the LDA model from here. And this is so easy. I'm just going to say, I'm going to define my LDA model. So the hyperparameters that you need to do LDA is that you tell it how many clusters to build. That's K. So I'm telling it do make 20 clusters in this vector space, and how many training cycles you want to do. So I'm saying 12, but you can do however many you want. And then you just say fit this to our vectors that we made and run it. And it's going to take a second to run it all. It's a lot of computations in the background. And if you're playing along at home, feel free to try with a different number of clusters or a different number of iterations and see how the results differ. Okay, so that took 16 seconds to build my LDA model over 13,000 records. And now here comes the fun part. I'm going to look at the words that are most strongly associated with each topic. So 5 words per topic. This big old line here is just a way to make this print out in a human readable format. So here we go. These are our clusters. They're different every time. But you can kind of look at them and see how our model is doing at pulling out topics. So like, let's look at this one. This looks like a railroad one. It's got cars, which is probably railroad cars, Pullman, layout. There's a lot of engineering documents. This one is fun. This one comes up a lot. This is the Chicago Women's March in 2017. They have a lot of photographs from the Women's March. This looks like another one about railroad engineering. We're looking at ducts and drawings of railroads with airflow. Let's see if there's another one. Oh, here's one, history one. Custer battle Little Wheelers. It's probably the Battle of Little Bighorn with General Custer. So yeah, so you can kind of see that this is starting to be something that might be useful. And if we wanted to, we could go back and tweak it and tune it until we came up with something that was a little bit better. All right, so oh my goodness, we are coming right up to the end of the hour here. Michael, I'm gonna pass it to you.
I had a little section about running Spark in the cloud, and I can summarize it by saying that if you use a public cloud that offers platform as a service offerings, you'll most likely be able to run Spark there, which means that you can press a button and a big Spark cluster will spin up in the cloud, and you can run literally the same code that we were talking about here. So that's an opportunity for you to use it in production across large data sets, even if you don't have big compute resources pools in your institution. Do you want to wrap this up, Audrey?
I think that we should just leave the space for a little bit of questioning at the end, if anyone has questions for us or comments or things that they want to share. Again, we'll make this the slides public. So if you were really hoping to learn about the deployment to the cloud, and I cut Michael off of his last 5 minutes so he wasn't able to, then you can look at the slides or feel free to reach out to us and we can talk to you about it too. But thank you so much, everybody, for coming and joining us today. And I hope you had a good time. And again, if you grab our email addresses, grab our Twitter handles, and be in touch if you want to talk more.
Thank you, Audrey. Thank you, Michael, so much. It was very clear and very impressive and very inspiring. Thank you. Thank you again.